Good evening. Welcome back, everyone. It is our September Speakers Night for 2025. It's already September. I can't believe it. Welcome back to the show after the summer break. I can't believe it's over. Welcome to Rask Toronto Center. We are online tonight, and I am Dr. Elena Hyde, the second vice president of the Rask Toronto Center. And actually, little fun fact to start us off, I'm joining you tonight for my very first broadcast as a Canadian. Welcome, everyone, to our Speakers Night presentation. Please note that this meeting is an online only presentation and not at our new York University meetup location. Our president, Scott Masterton, will be talking about various programs later on this evening. But first, we have a very special event to kick off, and I always start these events with a land acknowledgement. So I'd like to go ahead and start off by acknowledging that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here, together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, for the main part of our broadcast tonight, of course, I get to introduce our wonderful speaker, um, joining us from far, far away, well, maybe not that far, depending on what part of Canada you're in right now. Dr. Jennifer Andrews, currently an associate astronomer at the Gemini Observatory in Hilo, Hawaii. That's right, the famous Gemini Observatory. She's joining us tonight, and she received her PhD in astrophysics from Louisiana State University in 2011. She's had positions at UMass Amherst and University of Arizona before finally settling on the Big Island next to the Big Telescope. Jen is an observational astronomer concentrating on massive stars and their deaths as supernovae. And galactic astronomy at Gemini has all kinds of aspects, but I have to say, these really giant supernovae are just on a whole different event scale. When Jen isn't doing research and helping keep an international telescope running, she enjoys trying to grow interesting tropical plants, I believe, which I guess you could do there, volunteer work, and keeping her cats out of trouble, which I personally can identify with a great deal. Speaking of trouble, of course, I understand that tonight she is going to tell us about troubles of a whole different scale, super troubles, if you will, or perhaps. Jen, please take us up, up, and away and tell us all about it.
Great. Thank you so much for having me. Hello everyone. I'm going to talk to you today about supernova forensic files. If you're like me, you fall asleep watching forensic files, and I thought this was a great way to tie it in and to understand how we actually can use the explosions of massive stars to learn about how the massive star lived itself, which is a very great tool because this allows us to understand massive stars outside of our own galaxy. So that's sort of the theme of the talk today. And so I'll walk you through the research I do and some of the really interesting things we're doing both from the ground and space to understand more about how massive stars live and die. But I would also first like to start. First, I would on this title page, there is a supernova. So just kind of have a glance and keep in your mind. I'll reveal to you where the supernova is in an upcoming slide. But I also too would like to do a land acknowledgement. So I work for Gemini Observatory. One of our telescopes is on Mauna Kea, which is a very sacred mountain. I am allowed to do amazing work in a wonderful location, and so I always want to make sure that I acknowledge the land that we are using and its importance to the Native Hawaiian people. Okay, so this is a very similar photo to this was actually taken with Gemini Observatory. So this is a great image that we took before and after. And you can see that in one of the lower spiral arms, And I'm not sure if my cursor shows up or not, but I'm going to circle it here. You can see that there's nothing, 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 and then there's something. And okay, so this is a nearby supernova 2023 IXF. And what all these numbers mean is that it was discovered in 2023. And IXF is just the code number, meaning that it was found later in the year, because you name a supernova. The first one in the year is A, A, B, C, and then A, B, A, C, and so forth. So this is IXF. So that means we found lots and lots of things before we discovered this one. And when you break that down, it actually means that a supernova explodes about uh, about every 10 seconds, one supernova in the universe explodes. And so that means that there are a lot of events. Now, we have to put caveats on this, and that, yes, they could be exploding every 10 seconds. The universe is a very large place. So we are limited by the volume that we can actually see. So we're only seeing a very small percentage of those. And then of the ones that we're seeing, most of the ones that are very close to us, of the ones that are further away from us, we are only seeing the brightest events. And about 2/3 of those observed supernovae come from the deaths of massive stars. So there are multiple ways that a star can end its life. And there are two types of supernovae that we talk about. And one is core collapse supernovae, which is what I'm going to discuss. And it comes from massive stars whose core collapses. And so about 2/3 that we're seeing are from these massive stars. On the other hand, there are type 1a supernovae that are very, very useful in cosmology. They have very similar properties that allow you to figure out how far away they are. But those need a white dwarf and some other companion. So I'm not going to be discussing those. I'm just going to be discussing the deaths of massive stars. And so this is a really nice plot that I like to show that just sort of gives you an idea of the sun. So up here in the corner, the size of a sun compared to an O star. So an O star is the most massive kinds of stars that we have. And in the middle, because I will be discussing this a little bit, is a Wolf-Rayet star, which is a massive star that happens to have very strong winds, which means that it has high mass loss, and they will often create these beautiful cocoons. But these, in fact, the Wolf-Rayet stars create a lot of the atmosphere is stripped off before it explodes. And so the supernovae from Wolf-Rayet stars are often different from just a normal O star. So what hopefully you will understand by the time I'm done with this talk is that while massive stars are massive and bright and easy to see, the ones in our galaxy from Earth, we don't know much about them because they don't live very long. They don't live fast enough, or they live almost too fast. So finding them in different parts of their evolution is difficult. And the whole point of my talk is, how can we understand what goes on in a massive star before it collapses when we don't have straight observations of what's going on? So we can use the explosion itself to understand maybe what had happened in the past. Let's move forward. I like to show this because, as you all may know, James Webb Space Telescope was launched a few years ago, and the data coming out has been phenomenal, more than we could have ever asked for, better, and just beautiful. And this is a beautiful image that was being taken of the Cartwheel galaxy. It was already in an early release science program, which meant that they had queued this up. They knew this was going to be observed. And then very soon before it before it was observed, a supernova went off into it. So 2021 AFDX was one of the first ones that were supernova that were discovered or seen with JWST, and it was purely serendipitous. It just happened to go off, and then they just happened to take an image. So everyone, supernova scientists, all astronomers, were very excited about this, and to see what sort of image quality and the fact that we were getting these beautiful mid-infrared observations that we had not been able to get before. So I love to show this picture. It's very pretty. All right. So let's just kind of put this into context. So if you go back about 160,000 years ago, the Earth was experiencing an ice age. Homo sapiens were arriving on the scene in Africa, and in a very nearby galaxy to Earth, a star explodes. And the star explodes in the Large Magellanic Cloud. So this is an artist rendition. We can't see outside of our own Milky Way to know exactly what it looks like. Um, but this is an irregular galaxy, very, very close to our own Milky Way. This star exploded, and then in February of 1987, the light finally arrives on Earth. And this object is known as supernova 1987A. Unfortunately for us in the north, the Magellanic Clouds are only observable in the southern hemisphere. So this was a great event for naked, and it was observed naked eye easily from the south, and a wonderful event. But in more ways than one, this was an amazing event for astronomers, for massive star astronomers and supernova scientists specifically, because it happened so close. We haven't had, and I'll discuss this later on, we haven't had a Milky Way supernova in over 400 years. So this was the best example of a chance of us to watch a supernova evolve very nearby and in real time. But the most exciting part, I think, for a lot of people was the fact that the star exploded, but because the LMC is so nearby, we were able to use pre-explosion images. So we were able to go back and look at the images that were taken before it exploded, and could figure out which star it actually was. So there was enough, and this was prior to prior to Hubble Space Telescope. So this is just ground-based imaging, and the star was a bright blue star that they were able to pick out and figure out that it, in fact, was the one that exploded. Now, this means that unless you have images of an area before the star explodes, and it has to be very good images, you're not going to be able to see the actual supernova. And that leads us to the fact then that we need some other ways for most supernova to figure out what kind of object exploded, because as you get further away, you're not going to be able to detect them from the ground or space, as they happen in maybe rare galaxies, or small weird galaxies that we don't have a lot of great images on. If supernovae happen in beautiful spiral galaxies, we often have lots of images of those because they're very important for understanding star formation and lots of processes that happen in our own Milky Way. But as I mentioned, HST was launched. And so now, at least, we have a beautiful library of pre-explosion images. So these are all HST images where there's been a supernova, and we've gone back and looked, and we found what star exploded in the HST imaging. And depending on how many filters, depending on how many epochs, we can get an idea of how the massive star evolved. But often, there's maybe only one filter. There's only maybe one epoch. And so you kind of get a quick snapshot of what the star was doing, on February 2007, what it was doing hanging out that day, but not know, maybe what it was doing in the 1500s. So you just get this quick little snapshot. And these only work for the closest galaxies. So this is the most direct way to do forensics on the supernova and see what exploded, is to go and look and see what was there and then what wasn't. So you can see in all of these, there is the supernova that is later on. So you can see the actual bright event, and then you go back and look and see what lines up at that location. Much easier if the galaxy is right nearby, because your resolution is a lot better and you can differentiate many, many stars. As you get further away, sometimes maybe it's a group of stars instead of a single star. So even if you have all of this beautiful data that exists in the archive, it can make it very difficult to figure out what actually exploded. And of course, this is getting easier and easier with time, because we're building up this library of images that are taken doing all sorts of different science. So most of these images weren't even taken for supernova science. They were for all kinds of other science, but we as transient astronomers use that just to see what was going on before the supernova happened. So basically, to summarize, you have to be very lucky to have pre-explosion imaging. So you have to rely on other methods to help understand the mass loss from massive stars, to help understand what's going on right before it explodes, to help understand why it explodes. So to delve into that more, we need to figure out how a star actually, a massive star is formed, and what leads up to its death. So this is a beautiful HST or JWST image of a star forming nebula. It's like a nursery here, and near it's part of the Carina Nebula, and so you can just see this absolutely beautiful JWST image. And this is a stellar nursery, and why that's important is because um, all the stars are going to be forming in this star forming nebulae, and depending on how massive a star is created, the star will sort of evolve onto two different pathways. And these are very, very bare bones, but this just gives you a great overview of what happens. So stars like our sun, and a sun is one solar mass, so that makes sense. So stars less less than eight solar masses, or eight solar masses and above, we call a massive star, and below that are low mass stars, and then so a sun-like star is one solar mass, and it takes billions of years, and it will evolve into a red giant. So our sun will become a red giant at some point, and then it'll just slowly lose its atmosphere as a planetary nebula and leave a white dwarf. Whereas a massive star shines bright and lives a very short lifetime. So instead of billions of years, it takes about millions of years for it to run out of its fuel. It becomes a red supergiant, like Betelgeuse, you may recognize in Orion, and then it becomes a supernova, where you end up with a black hole or a neutron star. And then at the point of death, what's wonderful is that all this material goes back into the surrounding interstellar medium, circumstellar medium, and it creates the building blocks for more stars. So massive stars are very important, and why we actually care a lot about how they evolve and how they return their material into the surrounding environment, is because they are great recyclers, and they take hydrogen and helium and they rapidly turn them into heavier elements, and we need these heavier elements to form planets, to form life. So massive stars are incredibly important for that. Now, when you think about massive stars, if you think about looking up at the night sky here, a lot of what you see are massive stars, or they're just nearby low mass stars. So the closer they are, the less bright they have to be for you to think of them as bright. But when you take a sample of, say, 300 or so stars, and you put them into bins, only about one of those stars is going to be more than 10 solar masses, whereas 50 of them would be about the mass of the sun. So there are way more low mass stars, but the high mass stars can be brighter than thousands of the low mass stars combined. And so you have fewer massive stars to begin with, and then they don't live very long, because the more massive you are, the shorter your lifetime. So a 10 solar mass star might live 30 million years, whereas a 60 solar mass star might only live about 3 million. So there is less of time. There will be less stars in the evolutionary state that you want to observe. So it makes it much harder to actually observe the massive stars. And then they have to be in our own Milky Way mostly. When you have a supernova go off, it can be in much, much further galaxies for you to do the forensics and figure out what actually exploded. And so, like I was just saying, because there are fewer massive stars and because they live much shorter lives, we just don't understand as much about their mass loss or how they have evolved right before they explode. And we really want to, because the ionizing photons that come from these stars, the heavy elements that come from these stars, are extremely important to life as we know it. So what actually is holding a star together, whether it is a massive star or not. For the most part, there are two forces working. So you have um, the core where you are fusing hydrogen into helium, and that is creating pressure that exerts outward, whereas you have gravity of the actual envelope of the star pushing down. And so there's just this hydrostatic, this balance that happens that keeps a star um, as an actual star. Um, Sometimes the core will move into fusing heavier elements, and then it takes a while, and then all of a sudden gravity and pressure sort of have to eke it out a little bit. The heat will make um, the envelope expand, and then that's how you get these red supergiants. And then after a while, it cools, and you get smaller stars. So it's just a constant battle. And then eventually, as you have run out of hydrogen and helium, you start the process of core collapse. And how that works is that once you're in your supergiant star phase, so you have burned all your hydrogen and helium in the core. So about, for a 10 solar mass star, or, a 30 solar mass star. So say you're doing 10 million years fusing hydrogen and helium. Well, then you have to switch and you fuse helium into carbon, and that takes about a million years. Then you have run out of helium, so then you're fusing carbon into neon, and so that brings you down to about 300 years. Then for only 6 months are you fusing neon into oxygen, and then about a week of oxygen burning into silicon, and then silicon into iron. Okay, maybe that lasts like a day. And then once you get to iron, um, that is when the actual core collapse happens. So any element heavier than iron, it requires a death of a star of some amount. So a good way to show this, this is a great periodic table, is this periodic table is showing where the heavier elements are coming from. So hydrogen and helium we got in the Big Bang, mostly hydrogen, tiny bit of helium. But high mass stars are responsible for a lot of different elements: sodium, magnesium. You can see all of these here. There are other events such as merging neutron stars, that if you've been following any LIGO gravitational wave sorts of news, these would be where you start making your gold, your silver, various things like that. But to get to a neutron star, first you have to have a massive star explode. So it all kind of goes back to massive stars. So hopefully I'm making the point that massive stars are extremely important to our universe. But one thing I haven't necessarily mentioned is that massive stars aren't alone most of the time. In fact, we believe most massive stars form with buddies. And this is really important because that means that when we are now looking at, if we're finding stars in pre-explosion images, if we are looking at supernova explosions, we now have to think about, okay, maybe there is a companion that is changing what we're seeing in the aftermath, or how the supernova itself is evolving. One of I think the coolest massive stars that has a companion is the massive star Eta Car. It's in the Carina Nebula. So, okay, the cosmic cliffs here is what I showed you earlier, the stellar nursery. Once again, this is down in the south, so we can only really see it well from the southern hemisphere. But in the mid 1800s, it had this massive explosion eruption event that was observed actually by William Herschel. So there are actual written down observations of this event. So before we had really any new new observatory types of things, like there were maybe some glass plates, I think, taken possibly, but mostly just by eye observations. And it's this homunculus nebula here, so this kind of hourglass looking event. So this is now an image that was taken, I believe, with HST. And then you can sort of see this big nebula, and and all of the material around it. And in fact, it's 120 mass total system, 120 solar mass total system. What that actually means is that eta Car is a binary. And so there's eta Car A and eta Car B. And like I showed you at the very beginning, eta Car B is actually a Wolf-Rayet star, we believe, and then eta Car A is an O star. And they're on this very weird orbits that are very elongated. And this affects, so the period is about 5.5 years, and this eta Car B actually passes inside sort of the atmosphere of eta Car A, and so every 5.5 years we see really interesting things happen. But the question is, how do we get this very long, this weird elongated orbit that happened after there was an explosion? So eta Car exploded, but the stars were still there. So what sort of energetic event can cause that bright explosion to be seen from Earth, and that would cause all this material to be surrounding this massive star system? And as you can see here, so this video here is just actually various HST images throughout the years, and you can see it's just taken on eta Car, and you can see all the material flowing out of it. So we know that there was some event that obviously that created the homunculus nebula that allowed a lot of energy to escape, and then a bunch of solar masses of material as well. Oh, and just to sort of keep it, just to have an idea of the size we're talking about. So this is the sun in comparison to eta Car A, and if we were to put the sun at eta Car A, then eta Car B is roughly at Mars distance. So they come in very, very close. So what do we think happened to actually create this event? And one of the ideas put forth is that, in fact, the eta Car system was a tertiary system. And what happens is, as stars evolve and their atmosphere can expand and contract, eventually, if a star comes nearby, its companion comes nearby, it can strip off some of the atmosphere. And then that changes sort of the dynamics and the orbits, and you can transfer momentum, you can transfer lots of stuff. And so we think what happened is there was an actual merger event that created the explosion from from two of the three stars, and then the way it swung out the other eta Car B. Now this can explain sort of the nebula itself, and this very weird orbit that we see around it. And the reason that is important is because massive stars don't they don't form alone, and so we need to understand that this can possibly happen, and think about if eta Car actually explodes now, it's going to have to explode in all of that material that it released 200 or so years ago. Okay, no, next one. Next slide. All right, there we go. Here's another really awesome example. This is a JWST image of this beautiful Wolf-Rayet star that actually was found to have these concentric rings around it. So I just want you to also think, okay, that this star exploded. How is that interaction with all of these different rings of dust? How is that going to look to us here on Earth? And how is that going to change how the supernova evolves? And this just was, I don't want to say baffled. Often there are headlines that are like, astronomers are baffled by this. We weren't baffled, but we were just very surprised to see how obvious these shells showed up, and how it was very much actually explained by a scenario like this, to where there is a companion, and as the companion comes by, there's a stripping of the envelope of one of the stars, and then each time there's an orbit that's completed, then you just give off another bit of your atmosphere and a bit of your atmosphere, and so you start to create these concentric shells that are showing up. So it's a pretty good explanation, and the fact that this massive star must have a companion nearby. And I keep alluding to this because this is sort of the meat and potatoes of what I'm actually working on and what my research is on. If you have all of these various dust shells around, and you have a supernova explode, then there's going to be clouds of gas and dust that the light from the supernova is going to have to go through. So this is just a really great figure that shows if you have just a white light source, like a light bulb, you're going to have a continuous spectrum, or and where wavelength and brightness, you have this. But then if you introduce a cloud of gas and dust between you, also, I apologize if you can hear, hopefully you cannot hear the rooster in the background here, but if he is really, really enjoying my talk outside. So I apologize for that. So when you introduce a cloud of gas and dust, then you can have an emission spectrum. So where the light and the excites the atoms in the clouds of gas, and you get these emission spectrum. So if you're looking across the wavelength of light, so it goes from short to long, then you would see little spikes instead of a smooth continuum like this. You would start to see little individual lines. And if you're looking from a different direction, after the light passes through, you can see absorption. So you can actually take these spectra and look at the supernova and see what elements are there, and see how broad they are, and what you can actually, you can understand the material that the supernova explodes into, which is the material that was on the massive star, and it's what the star had been fusing for the past million years. So you know what the composition is, so you can use this really great tool. And the thing that is sort of that you need to keep in mind is that the supernova has kind of two components. The explosion happens, and so what happens then is you get this what we call a shock breakout, where the light and the neutrinos escape, and so you get this really bright flash that is, very, very short. And then you have both a light front and a shock front move forward. And the light is obviously going to be moving at the speed of light. The shock is going to be moving at the speed of the supernova expansion, which is, between 10, 20, 30,000 kilometers per second, and then it'll slow with time. So if you, like I mentioned before, if you have it explode and there's material around it, and you take an observation within a day or two of explosion, then you can very easily see elements that were made in a massive star and was in the surrounding material. You can see how strong they are, and that tells you how much of the material is there. It tells you how energetic the explosion is, because you need a certain amount of energy to ionize certain materials. You can see how wide they are, and that tells you how fast they're moving out, or how fast they were moving when the star exploded. So that would tell you, okay, if I have a companion, then maybe our wind speed is going to be a lot higher than if I was just a single massive star just losing a slow wind, and my wind speed is 10, 20 kilometers per second. So this is an incredibly useful tool, but it's even more useful when you take a lot of spectra in a small amount of time, because the light is moving quickly. It's very quickly moving through the circumstellar material, the material that's around it. It's moving at the speed of light. And like I said, the shock itself is maybe only moving at 10, 20,000 kilometers per second. And so what I'm showing here, which is an amazing bit of science that we were able to do a couple of years ago. This is the supernova that I showed you at the very start, the 2023 IXF. And the color coding is the earliers are more purple, the later time are more orange. And so as you go down, you are going at your later time observations of your supernova, but that means you're going back in time of your mass loss for your massive star. So you're doing forensics, and you are seeing, the first spectrum you take is the material that was lost the soonest before explosion. And then as you go with time, you get material that was lost, or that's further out, that was lost, millennia or decades ago, centuries ago. So you're able to, with each spectrum, you're able to look back in time and see the material. You can see how the explosion itself is changing. And so you can see here in particular, one of the things we notice is just over a few days. So this is over one day is like at the dark color. 3 days after explosion is the yellow color. And you can see there are lines that are that exist early on that disappear as we sweep out through material, that lines might get narrower as we go on with time, that some might completely disappear. And this is just an absolute wonderful set. And you can sort of see, so if the purple is if we're just sampling the light that has just gotten here, the sort of darker pink is a little bit later on, and then by the time we get to the salmon color, and then so by the yellow time, this is 3 days later, and the ejecta is probably at 25 Earth orbits from the star, whereas the light is maybe 520 Earth orbits. And so we're sampling a completely different region, and we're seeing more and more of what was lost by the massive star before explosion. Now, if we keep going on, so this is just the first 3 days, and you can get a lot of information, especially the first week. And this is just the optical. You can get different information in different wavelengths. So if you go into the UV using HST, you find completely different lines and see a lot of different, especially early times, because supernovae are very bright in the blue because they're very hot. And so there's lots of lines in the UV. And then out to the near infrared and the mid infrared. So you move on to JWST, and you see lots of different things happening there. But if you keep observing after a year or two and it's gotten fainter, what happens then is that you start hitting material that was lost well before the star exploded, and you start to see features that show up in your spectra that you can only see if there is material that the supernova is interacting with. So when we generally take a spectrum, an emission spectrum, we see a Gaussian bell-shaped curve, because it's just expanding smoothly outward. But if, say, there are clumps, if it's not a shell, if it's asymmetric, if there's bits and pieces of material out there, if we wait long enough, the supernova shock will interact with it, and we'll start to see really interesting features in our spectra that tell us, okay, so at 500 days, all of a sudden we see a very kind of boxy looking shape. And okay, the supernova was moving at 5,000 kilometers per second. We can do, velocity times time and figure out, at what point in the past would this material had to have been ejected and how far away it actually is from the supernova. So we get a ton of information just by following it long enough. And nowhere is this even more apparent than if we go back to that supernova that showed up in 1987. So here's a nice time lapse of images starting in 1994 and then moving onward, and you start to see these beads of light light up. So as the ejecta is running into the material that the supernova has lost, and I'll play that one more time because it's really beautiful to see, it is illuminating this ring, and you are starting to see the material light up. Now, for almost all supernovae, we do not have this resolution. It is not nearby. We are not going to be able to watch in real time and actually resolve the ring around. But if we get optical spectra, we can have an idea of what's happening and go back and come up with a model of how the environment actually looks and what could be causing a ring. Generally, it's a companion, we think. And so we get a lot of information about the stars that exploded by looking at the explosion itself. Now, here is the most updated JWST image of supernova 1987A. And you can see there are, and some of you might be familiar with the inner and outer ring. So it's like an hourglass, and then the inner ejecta, and then the hot spots here that I was just showing you. And lo and behold, there's been some papers out that are using JWST and see like these very bright regions. So this is an argon filter, or this is an argon emission line. And because that argon needs a lot of, it needs a high power source to excite it enough to be seen, they believe then that is proof that there is a neutron star that is now where the supernova was before it exploded. which would be one of the first times we can definitively say, okay, this was a star that exploded and now there is a neutron star that's left there. So very excited to see what more information we can learn about 1987A from JWST. Okay, so obviously the easiest way to understand what explodes and to actually look and see in real time, or at least real time as the light travel time to Earth, is to have a supernova explode, as you can see from 87A, as close as possible. So having one in the Milky Way is really going to be our absolute best bet. But it's been about 400 years. Okay, so there are historical supernovae that there is documentation. Supernova 1054, there's cave and rock paintings in various parts of the world that show that there was a new star near the moon. So this was bright enough to see from Earth easily. I'm not sure if you could see it in the daytime, but you could definitely see it at nighttime. And then Tycho's supernovae in 1572 and Kepler's in 1604. And what's really great about having this historical record is that we can find these events now and look at the supernova remnant and also gain information about the stars that exploded there. So will we see a supernova in our galaxy anytime soon? Because we expect one every century, roughly, and so we're very well overdue. And one of the best candidates is Betelgeuse. And if you don't know, it's one of the armpits of Orion. It's the red star. It's easy to tell that it's red. And if you remember a few years ago, it dimmed quite a lot. And that was because it had a bunch of dust that it was created that just went in front of it and made it dim. You can sort of see the comparison between Earth's orbit and Jupiter's, and I think this is a better picture here. So Earth orbit here, so Betelgeuse would be this bright yellow thing, and then we have Earth's orbit and Jupiter's orbit, and then Saturn's orbit here. So you can see how large it was. So now, if Betelgeuse exploded, it would be as bright as a full moon. So you would be able to see it in the daytime for a few months even. And then if we did the math and the light travel time, it would have had to explode in 1400 AD. Now, what's really cool is there was a couple of grad students when it had this dimming effect and people were like, oh, it's going to explode, it's going to explode. They created this really nice graph of time since explosion here and then how bright it is. So the full moon is at this brightness here. Venus is here. And so we know we can see Venus in the evening and the morning really well. And sort of this is how its average brightness is. So for, a few months, it would probably be between the brightness of Venus and the moon. So you would be able to easily see it in the daytime. And then it would take almost 3 years to get back down to its normal brightness. And then eventually it would fade away and all of a sudden Orion would not have its armpit there. So we know Betelgeuse will explode. We know that it's going to happen at some point. We just don't know when. And it soon means it can happen tomorrow, or it can happen in 1,000 years, it can happen in 10,000 years. So we're not exactly sure. But what is really interesting that we've learned about Betelgeuse in the past year is that, remember, I mentioned we think most massive stars have buddies. For the longest time, we did not think Betelgeuse had a friend. But just recently, there was imaging taken with Gemini North that claims to see a very faint companion near Betelgeuse. And this would fit in with our theory that most massive stars have companions, and explain maybe why we haven't seen it. But expect a lot more papers out and news articles out about whether it does, whether it doesn't. But it's just a very interesting tidbit that a star in our own backyard that we thought we knew everything about maybe is still hiding some secrets for us. So I just want to end there and with a very important message that many of you may recognize is the fact that we are all made of star stuff. So we have to have massive stars explode to create these very heavy elements that we can actually create planets, we can create our DNA, we can create apple pies, and everything we need to live here on Earth and in this universe. So thank you very much, and I will be happy to take the questions now.
Oh, wonderful. Thank you very much, Jen. This has been a great talk. I think, those galactic fireworks are a great celebration to restart our speakers' nights with. I'm really hoping that you get to see a lot more of these and then share the pictures with us. And of course, hopefully none of them are too close. It's special, I suppose, special, was it 6.2 billion year shout out to Wolf 1130. Um, but we got some questions over on YouTube, so they're going to be coming in now. I hope folks who are listening will type their questions in. It looks like we have one that's arrived already, so I'm going to give you this one first. This one comes in from Zapfan. Any new signs that a supernova happened shortly before the formation of our solar system?
That I'm not 100% sure of. I haven't followed up on that, but generally, you can look at, especially with sample missions that go out and take, yeah, pieces of asteroids, various other rocks in our own solar system, and they can look at the isotopes and see, that there are certain elements here that can only be here if there had been a supernova in our vicinity. Um, and I mean, the odds of there being a supernova prior, well, obviously there was a supernova prior to the solar system formation. It's just the question is how close was it, and the did the actual like shock maybe from that explosion help compress the solar system and to help it form a little bit there. So that I don't know the full answer, but I know we can sort of look and we're understanding more and more about our own solar system as time goes on, while as we send out these sorts of missions and sample comets and asteroids and meteorites.
Yeah, absolutely. And I guess there's another, it's a comment, not a question. CDB 45 says, wonderful presentation, very interesting. Thank you. And I thank you as well. Well, we're giving people just an extra chance for questions to come in. I'll go ahead and ask one too, because I'm quite keen to know if you're have any thoughts about the announced quasi star proposal that they've come up with for these super, super, super big supernova.
Sorry, I missed the one special word before star.
Quasi star.
Oh, so these are stars that are what, over 300 solar masses or something, and they don't
Yeah,
have the
well,
right.
well, well over. These are the
Okay.
ones that, in theory, are large enough to contain, in theory, in large enough to contain their supernova, which would form super,
Oh,
super massive black holes. So
right,
I just thought I
right.
would throw that out there because it's been in the news recently.
I do not have a lot of background on that. I do know that there's still a lot we don't know about massive stars, and especially a lot we don't know about massive stars in the early universe, when the metallicity was very low and maybe weird things could be happening. So um, I think that they possibly did exist in the early universe, but I'm not sure if we have if they could exist at this point now, unless something like that formed in a very clean area of space where there was very few pollutants from heavy metals. I'm not sure. But I know that people are always looking for signs of this sort of thing. Um, and then, of course, I don't know if it would, this would shape up in, say, gravitational waves, if you would see something very interesting in that aspect, if you had a quasi star explode, if that would even show up and give you a new source of gravitational waves.
Yeah, absolutely. I know some folks are trying to link them to the little red dots in JWST, but it's just good fun. And since you mentioned cats earlier, it's almost named after my cat Quasar, so I had to throw that at you. Um, oh, and it looks like we did get an extra question on the chat while I was asking you that. Um, what's the name of your rooster from Julius Caesar?
So there are a few out there, but the one that makes the most noise, his name is Cluck Norris, and he is the boss of the yard. So But he's also the gentleman of the yard because when he finds delicious things, he calls the lady chickens over, and gives them little treats. And to be clear, these are not chickens that I own. These are feral chickens that just like to live on in my yard. So I now have adopted them.
Well, we're getting some suggestions from the YouTube chat about what might be the correlation between supernova neutrinos and the rooster.
Yeah.
So, um, since, we'll go ahead and leave that to your expert opinion to see if there are any, can we use this as a supernova detector, maybe? Um,
Which is
and
one thing actually I would love to mention is that if Betelgeuse was going to explode, our neutrino detectors would pick up on it, 6 hours or so before it actually exploded. So we would know that an event was coming from the neutrino detectors, which are they're much more advanced than they were for 1987A. I think we detected 20 neutrinos in 87A, and they had to actually go back and dig through the data and say, oh yeah, here it was. Um, so we will have an advanced warning. We will know that it is coming from the neutrino detectors. We just maybe won't know exactly what star is going to explode. So we would just have to keep our eyes open. And another fun fact is that Betelgeuse being so bright, or big telescopes like Gemini won't really be able to follow it. So we will rely on small telescopes and amateur astronomers in particular to really get data for us if Betelgeuse does explode anytime soon.
Excellent. Yes, I think all of the amateur astronomers from RASC will be putting their hand up to volunteer immediately.
Perfect.
And we just have one last question that snuck in, so I think we have time for this one. From Ralph Chu, what processes would form ultra heavy elements like uranium?
So that's okay. I am not let's see. Can I scroll back to let's look at our periodic table. Um, let's find out what oh my goodness, I get stuck here. Yes, so I am not a chemist by any means. And I definitely do not see uranium in my spectra that I take of stars. Um, Okay, now I'm going to show how much okay. So it looks like uranium has to be created from neutron star mergers. So yeah, you have to have two exploding stars that then merge together to create uranium. And so you can thank uranium that powers power plants on Earth from the merging of two neutron stars.
Well, on that merger of exploded stars that for everything that's happening. I think we've got all kinds of things we could keep talking about, but we probably just out of time. So I'll go ahead and let everyone know if you're on YouTube, if you're got last minute questions and we didn't get to them, feel free to post them. We can always share this video again later. And I'll thank our speaker again. Thank you, Jen, so much for coming out today. It's been wonderful to hear your talk and share the excitement. And I think everyone now is really excited to find out more about those amateur astronomer opportunities as well. So normally I would go ahead and take off this moment to transfer one last time. So this is the last transfer of the evening. We would normally go over to the president of the Rask Toronto Centre, Scott Masterton, to finish off the evening. However, I believe we do have a small internet glitch tonight. So instead, I am going to finish off the evening much, much quicker and just remind everyone to think about going over to the Rask Toronto Centre website for events. And if you haven't been there before, it's raskto.ca. That is where all of our events are listed. And because our president isn't here tonight to send us off properly, I'm just going to say thank you everyone for joining us on this wonderful exploration. Please see the Rask Toronto Centre website for all of our events, upcoming and otherwise, star parties, awesome additional speakers night next month, and all kinds of great stuff. This is Dr. Elena Hyde, and it's been really, really fun having you all here to share in this great supernova explosion, starting off our talks again. Thanks, everyone. Clear skies, and have a wonderful evening.